Well, thanks for coming, everyone. My name is Major Jim Ployce. I teach at here, but not here when I'm there, at the United States Military Academy, specifically in probability and statistics. And I'm going to talk to you today about a project we did in conjunction with the Pennington Bioresearch Lab at LSU, as well as Fort Jackson, in trying to predict some body composition and some machine learning approach that we did here. So we have, all right, so some background to this. We were looking at trying to measure body composition, and to do that requires some very well-maintained equipment, a lot of licensed personnel, and carefully conducted protocols. And so we are trying to rely on these mathematical proxies to estimate the components of body composition. Specifically, we do a lot with BMI, with waist circumference and body weight. But there's been some new trends and new technologies that allow us to not have to necessarily use these mathematical proxies anymore. Specifically, the 3D body image scanning, and that's what we are looking into. So these 3D body image scanners, the one that we particularly are focused on is built by Human Solutions of North America, and it's this 3D body scanner that the people stand in the scanner, and it takes about 20 seconds to scan up and down their body, taking 161 different measurements of their circumferences and lengths throughout their body, anthropometric measures, and it's all automated, so it eliminates most of human error as long as they're not moving too much, and so it creates some very strong data points. This is an example of some of the measurements that are taken. Like I said, 161 of them on the human body. So there's been many studies done, including these two, that talk about the reliability of these things and how consistent they are, and giving some legitimacy to these 3D body scanners. So they are very well researched and do a good job of these anthropometric work. So our problem was how can we leverage data from these types of devices and then pair them with some health outcomes in order to look at a large data set and then pair it with a smaller data set using these 3D measurements, and to be able to infer upon some health outcomes in the end. So the problem that we run into is that to collect data at a research site in order to measure body composition in a large sample, one, you need the Human Solutions device, which is not inexpensive. We need some other methods of calculating, either DXA, which is like bone density, or an MRI scanner. We need to be funded to then collect the data on the individuals. And another limitation of many of these studies is that the people that take part in the studies are from the local area, generally. And it's not very time consuming. So we're trying to mitigate and get around some of these things by using data that is already at hand. Specifically, we are using data from Fort Jackson. So Fort Jackson trains 50% of the Army's basic combat training load of people, and including 60% of the females that enter the Army each year. So within these basic training recruits, we have about 21,000 people, 28% of which are female, and they're all scanned for uniform fitting. So they all go and use this Human Solutions machine to get their 3D scan. So we have 21,000 data points, and of these 161 anthropometric measures for every soldier. Okay, so that is a large data set that we're hoping to leverage. And again, these are some of the measures that they get: the body height, sitting height. This is the type of thing that we have access to now for those 21,000 soldiers. The problem with this data is that we don't have much for outcome data. So we know whether or not the soldier was chaptered. We know their physical fitness scores and some other chapter things, but nothing on the scale of physical measures. So no health-related body composition measures. And VICE the Pennington Biomedical Research Center, which used the same human solutions device, or the same model, but has a much smaller sample size, right? 21,000 in our Fort Traction training set device, that's 148 here. However, within this, we now have access to all the DXA measurements, so for percent body fat, resting heart rate, blood pressure, all these demographic variables that take part, that are present in the Pennington data set. Within the two, so you'll see we have our Fort Jackson data set and our Pennington data set, and the goal of this is to show so clearly the age is going to be a difference between the two data sets. However, we also know that for ages 17 to 21, once they've reached 17 to 21, the vast majority of the measurements that are being used are pretty static. They're fully grown at that point, so that's not as much of a concern. The BMIs are clearly a larger span for the Pennington data set and LSU than and we would expect that, than at the Fort Jackson. So, but they still, this range within a standard deviation encompasses what the BMIs are for our Fort Jackson training set. So PBRC has a lot of good outcome data, but the sample size is small. Fort Jackson doesn't have the outcome data, but it's got a really good sample size. So how can we leverage those two things together? So we're going to be using some of the techniques from this paper in Obesity Reviews on machine learning and obesity. Specifically, the techniques that we're looking at is clustering and principal component analysis. So those are the two elements that we're using. And we're pairing this with a paper. So this paper did a lot of really good work on looking and analyzing the different body types using these 3D scanning machines. And they found 13 different body archetypes. However, if we were to use those 13 archetypes on our 148 samples, it would be pretty challenging to get anything conclusive from it. So we're going to be building off what they have in some neat ways. All right. So our first goal, what we did was to look at principal component analysis and try to minimize or get these 161 measurements down to a more scalable number that we can use. So principal component analysis basically identifies what are the variables that are most heavily weighted within the data. So how can we take advantage of those variables to kind of creating new variables that are a weighted structure. They are a composition of all these other variables, and so that's the idea of principal component analysis. And each of those components can be thought of as a variable. So, as an example, if this is our BMI, right, and this is waist circumference, and we know those are related, we can take these and move kind of shift it down, right? We're going to kind of drop it onto a single plane, and now we have one plane that is instead of two, and so we've just cut the number of variables required in half based on some weighting of these two variables, which create this. So that's the idea that we're going with. The principal component analysis, once we go beyond component one, each of the follow-on components are orthogonal to one another, so they it's hard to visualize in 161 dimensions, so don't try. But if you have basically each of these different principal components will be accounting for some amount of the variance within our data set. All right. So why did we choose, or how many principal components did we use? We ended up choosing 5. So based on, this is a discrete plot that looks at how much variance each of these principal components account for. And so a common used method is the elbow method, right, where this is kind of like an arm. Not to be confused with the elbow measurements that we did. This is like an arm. We've got these kind of an elbow here. Now, we could have chosen 6. However, in the end, we did look at 6, and the clusterings remained the same if we used 6. So rather than add complexity for no added benefit, we went with 5. and the homogeneity of the clusters was much better with 5 principal components than 4. So that's where we rested on the number of principal components that we used. So then we have these 5 principal components, and now we want to cluster based on them. We want to figure out what is the general structure of the body based on these 5 principal components, or what are the 5 different groups that we can construct or really partition our 21,000 soldiers into for these clusters. So we use k-means clustering. There are lots of clustering methods out there. This research was done for the European Journal of Clinical Nutrition, and so that field is much more familiar with the k-means type clustering approach, and so that's one of the reasons that we went in that direction. But our goal is to kind of partition our data set into distinct subpopulations. Some other methods that we looked at. So PCA is one method that we looked at. We also looked at maybe we just want to cluster on all 161 measurements and do it that way. So we did look into that. We also looked into, well, maybe we do the principal components, but then we only look at the most heavily weighted variables of those principal components, and maybe that tells us something. So we looked at each of those methods, and we used what's called Mahalanobis distance, and that is takes into account covariance within the data set. And so we looked at that, and the smallest average Mahalanobis distance for these methods came with the one that we chosen. So doing 5 principal components, clustering based off that, and then going from there. So that's why we ended up going the direction that we did. So how many clusters do we use? Well, again, we can use our little elbow method, and we rested upon 4. Again, because we only have 148 clusters, we want to be able to have some interpretability in our final results. So 4 seemed like a pretty good elbow for us in our scree plot here. All right, and then our third goal. So once we've clustered all of this, we've clustered our Fort Jackson data set into these 4 clusters. Now we want to take members from the Pennington data set, and using the same weighting of the principal component and using the same clusters to then be able to assign these Pennington personnel into their respective clusters to then make some inferences about the population at large of the body types that represent those 4 different clusters, and evaluate, are there more poor health outcomes within a specified cluster. So we have some justification to cover here. So we need to justify whether or not using the principal component loading from Fort Jackson, whether or not we're allowed to do that with the Pennington data set. So that's one thing we need to justify. Another thing is we need to make sure it doesn't really matter how they're clustered. What matters is, are the clusters homogeneous? Are they like each other? And if that's maintained, then that's the goal. We want to have clusters that are like each other. So as long as we maintain that homogeneity, then that's a win for the extrapolation of PBRC, the Pennington data set, into our Fort Jackson data set. So to start, let's justify the principal component analysis. So is the loading from the principal component analysis on the Fort Jackson data set similar enough to the Pennington data set? And so what we did was we looked at the most strongly weighted variable from each of the principal components and compared them. Now, we only did the top 3 because visualizing in 5 dimensions, like I said, is not easy. So we stuck with 3, even that's a little challenging. But you can see with Fort Jackson, these are how the 4 clusters were arrayed across those 3 dimensions. And then when we do the same thing for the Pennington data set, it is the same general orientation. And if I could have contorted the plane, you'd be able to see it's on generally the same plane as well. So at least across the 3 primary principal components, our clusterings remain about the same. Then the next justification was, is the homogeneity of the clusters maintained? And so this is the average Euclidean distance across within the clusters for the Fort Jackson data set. And then this is it for the Pennington data set. Once we've taken those Pennington people and put them into the Fort Jackson clusters, you'll notice that only one of them, this is the only one where the Pennington data was slightly worse. All the other ones, the Pennington data actually was more homogeneous than the Fort Jackson data set, which was interesting. So we've ended up with clusters that are pretty good. So then now we get to visualize and take a look at what is it about these clusters that's unique, that's different. And so this is looking at the BMI within the Fort Jackson data set. So this is a violin plot which shows we've got an example of an outlier down here, right? The distribution of data, so the ends are the span of the data within each cluster across the clusters. And then the black box here, I think we'll see the diamond in the middle is the median, and then the black box is where 50% of our data lies. And you can see this curve kind of shows that distribution of how our data is arrayed across the four clusters. So this is the Fort Jackson data set. So now let's move this to Pennington, because the BMI is one thing that we did have common between both Fort Jackson and Pennington. And you'll see with the Pennington data set that certainly clusters 1 and 4 appear to have a lower BMI than clusters 2 and 3, and with some tests that did prove to be statistically so. But let's look at some other measures. So here's percent fat mass. So percent fat mass, much lower in cluster 4 than, say, clusters 3, 2, and 1. So they have a higher percentage of fat mass in these cluster 3. Lean mass, much higher in cluster 4, which is good, right? Lean mass is good. Lower in 3, as we would expect. And these are statistically different from each other by doing a paired t-test across the two using the correction on Bonferroni correction, there it is. Yep, okay. So we use the Bonferroni correction to make sure that we were, when we do multiple comparisons, that we're not overstretching our p-value, if you will, for those things. So then we have our VAT, which is really just like belly fat, and where you'll see a huge span in cluster 3 for these things, for percent VAT. High blood pressure, so the percent of high blood pressure, very low percentage in clusters 1, again clusters 3, high blood pressure, and cluster 4 has another higher percentage of high blood pressure there. So in conclusion, so we have these 4 clusters, and I think that what makes this research interesting beyond the outcomes here is the techniques of being able to take a large data set and then use some of the more expensive measures from a smaller data set and be able to make some conclusions that way. So it ended up being cluster 1 was primarily females, cluster 2, those with high BMI and low fat mass, cluster 3 was high fat mass, low fat free mass. So if you took total fat or total mass and subtract off the fat mass, you get the fat free mass. That's how that works. And then cluster 4, low fat mass, high fat free mass. In general, our body shapes in 2 and 3 have higher BMI. In clusters 3, they have high body fat percentage and VAT and a lower lean mass. And then the cluster assignments, what's kind of neat about this is we can program these cluster assignments into the human solutions machines and be able to have some idea of what their health outcomes may be coming out of a human solutions mapping like this. So I think that this is the team we have. So you'll recognize some of them. And they were great. This is our Fort Jackson team. We had some from Pennington that worked with us on this project. So with that, this is my contact information. If you have any questions, I should make that West Point EDU.
Thank you, Jim.
Yeah, thanks.
I ask you to make any comments you can on that picture.